Introduction to Mathematical Statistics. My name is Sandula, I'm a PhD student in Mathematical Sciences from Indiana University, Indianapolis. So today we continue with the solution of some exercises under the probability set function. Don't forget to subscribe and share the video with fellow grad students. So let's go straight to the question. So the first question, we have a positive integer from a positive integer from 1 to 6 is to be chosen by casting a die. Thus the elements C of the sample space C are 1, 2, 3, 4, 5, 6. So suppose C1 equals to 1, 2, 3, 4 and C2 equals to 3, 4, 5, 6. So if the probability set function P assigns a probability of 1, 6 to each of the elements of C, we have to compute the probability of C1, probability of C2, probability of the intersections, probability of C1, then union C2. So let's check the solution. We have our C1. We have first the sample space to be, let me just put in a bracket, 1, 2, 3, 4, 5, 6. Okay, then we have our C1 to be 1, 2, 3, 4. So, and then we have P assigns a probability of 1, 6 to each of the elements. So the probability of C1 for each of the element is, for this one we have 1 over 6. For the next one, how many times 2 appear is just 1, and that's also 1 over 6. How many times 3 appear in our 1, 2, 3, 2, 5, 6 is just 1, and that's 1 times 1 over 6, that's still 1 over 6. And then for 4 also we have 1 over 6, and that gives us 4 over 6, which equals to 2 over 3. And then for C2 we have 1, 2, 3, 4. C2 we have 3, 4, 5, 6. 3, 4, 5, 6. So probability of C2, since 3 appears just 1, that's 1 times 1 over 6, that will be 1 over 6. 4 appear once, and that is 1 times 1 over 6, that also gives us 1 over 6. 5 also appear once, and that is 1 times 1 over 6, which also gives us 1 over 6. And 6 also appear once, and that is 6 times 1 over 6, which also gives us 1 over 6. And this also gives us 4 over 6, which is equal to 2 over 3. So the next question, we have to find C1 intersection C2, and then the common element of C1 and then C2 is 3 and then 4, 3, 4. So the probability of these will be equal to 3 appear once, and then 1 over 6, and 4 also appear with the 1 over 6, and that is 2 over 6, which is equal to 1 over 3. So the next question is to find the union C1 union C2. So you can first of all find the union of those guys, or you can just use our inclusion rules and what that is convenience. Probability of C1 union C2 is equal to probability of C1 plus probability of C2 minus probability of C1 intersect C2, and that we have 2 over 3 plus 2 over 3 minus 1 over 3, right? And that gives us 4 minus 1, 3, 3 over 3, and that is equal to 1. Okay, and then I believe that actually make a pretty sense. So that's about question number 1. So you can just take your time and go through it again. So question number 2. So here's question number 2. So a random experiment consists of drawing a card from an ordinary deck of 52 playing cards. So let the probability set function P assigns a probability of 1 over 52 to each of the 52 possible outcomes. So let's say we denote the collection of the 13 acts and C2 denotes the collection of the 4 kings. So that's the compute probability of C1, compute probability of C2, the intersections, and then the union. Alright, then we have probability. Our C1 equals to collection of 13 acts. We have 13 acts, and then C2 denotes the collections of the 4 kings. 4 kings. So the probability of C1 of losing that will be 13 over 52, and probability of C2 that is also 4 over 32 52. So you will notice that in our playing card we have this, we have the intersection of C1 intersection C2 is that a heart also have a kings. So each of our flush have 1 king's heart, have 1 king's, and spade have 1 king's, club have 1 king's, and then heart also have 1 king's. So for this heart, diamond also have 1 heart king's. So that means that there is 1 card that is common to these 2, and that's I'm going to have 1 heart, 1 heart, and I'm going to write 1 heart, which is also a king. That means that the probability of C1 intersects C2 will be equal to 1 over 52. So their union now, probability of C1 union C2, that is probability of C1 plus probability of C2 minus probability of C1 intersect C2, and that is equal to 13 52 for 52 minus 1 52, and that is equal to 16 over 52, and that is about that. So you can also take your time to go through the solution again properly, and if you have any question you can just drop your comments in the comment section. Right, so the next question 3. This question is not okay. I think this question is not clear enough. Let me copy it again. Okay, we have a coin is to be tossed as many times as necessary to turn up 1 head. Thus the element C of the sample space C are H, TH, TTH, TTTH, and so forth. So let the probability set function P assigns to these elements the respective probability 1 over 2 over 4 over 8, 1 over 16, and so forth. So you have to show that probability of C equals to 1, and then let's C1 equals to H, HTH, dot dot dot. So we have to compute the probability of C1. Next, we have to suppose that C2 is that. So we have to also to compute probability of C2, probability of C1 intersection C2, and the probability of C1 C2. So let's first of all check how the probability is being assigned. Our sample collection, we have H for H, the probability assigned to our A is 1 over 2. For TH, we have 1 over 2 square, and that's 1 over 4, okay. For TTH, that's 1 over 2, 3. And then for TTTH, that's 1 over 4, dot 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 dot. So we have to look for the probability of the whole sample, and that will be the summation of k equals to 1 to infinity 1 over 2k. Okay, since our probability is moving in geometric series, so we have a form of infinity series. So if we take this, don't forget here our first term will be 1 over 2, the difference, which is our common ratio, so it's increasing by 1 over 2, So sum of infinity of series is given to be a over 1 minus r, and that is half times 2 over 1, which is equals to 1. So that's verified in this part. Okay, so the next one we have our C2 to be equals to h th, let me change the pen, C2 to be equals to h th t t h t t t and h, or t t t t and h. So for the first one, the probability of C2 equals to 1 over 2, 1 over 4, and then this TTTH is 1 over 8, that's 1 over 16, that's 1 over 32, which you can actually compute on your own. Alright, so and then for C3 we have for C2 we have C2, oh sorry, this should be for C1. Then for C2 what do you have? We have HH, we have T4 T's, and H, and then 5 T's and H. So this also should be equal to 1 over, that will be 2 raised to the power 4 5, that's 1 over 2 raised to the power 4 6, which you can also just to verify it and check the solution. Okay, so you can try to check the solution. This is 3 over 64, and then this is 31 over 32. Then you can confirm this. Okay, so the next question, we have to find the intersection C1 intersection C2. That is what they have in common. Let's check these 2, 4, 5. So they only have one element in common, which is T, 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 and H. And then the probability C1 intersection C2 is equal to 1 over what? 2, 5, 2 over 5. Okay, and that is equal to 1 over 32. So we have to find their union, PC1 union C2. That is just the addition, C1 plus C2 minus PC1 intersection C2. That's equal to 31 over 32 plus 31 over 32 plus 3 over 64 minus 1 over 32. So you can actually try to justify the solution to see if you get 63 over 64. So that's about that. If you also have any question on that, you can just drop it in the comment section. So let's go straight to the next question. So that will be problem 4. Problem 4, we have if the sample space of C is just C1 union C2, and if probability of C1 is equal to 0.8 and probability of C2 is equal to 0.5, so we have to find the probability of the intersection. Alright, next problem. So don't forget, probability of the entire sample space will be equals to 1. Right? So then the probability of C1 union C2 is equals to probability of C1, and that should be equals to 1. So by law of inclusion, probability of C1 C2 is equals to probability of C1 plus probability of C2 minus probability of C1 intersect C2. So we have 1 equals to 0.8 plus 0.5 minus probability of C1 intersect C2. So that means the probability of C1 intersect of C2 is equals to 0.1 minus, that will be 1.3 minus 1, which is equals to 0.3. So you can actually also confirm that, and if you have any question, you can also drop it at the comment section. So let's move to another question. That will now be problem 5. So for problem 5, let's see what we have. We have let the sample space be C. Our sample space should be given as 0 to infinity, and let C be subset of the sample space be defined by C, which is 4 to infinity, and then we take the probability of C to be integral of exponential minus x. So we have to show that the probability of the entire sample space is equals to 1, and then we have to evaluate the probability of C, the probability of its complement, and the probability of its union and then its complement. Okay, so let's first start with the probability of the entire sample space, which is equals to integrate the entire sample space. We have 0 to infinity exponential minus s ds. So if we integrate this, we have minus exponential minus s 0 to infinity, then you have minus integrate exponential minus infinity, then minus exponential is 0. So this actually decays to 0, and then this is equals to 1. So we have minus 1 and then giving 1, which actually prove that. Then the probability of C, now C is given from 4 to infinity exponential minus s ds, and that is equal to minus exponential minus x is 0, 4 to infinity. Also we have minus exponential minus infinity minus exponential minus 4, and that's equals to exponential minus 4, because this decays to 0, and now we have left with that. So the complement probability of C complement, that just been 1 minus probability of C by the definition of a complement, and that equals to 1 minus exponential minus 4. Okay, so probability of C union C complement, okay, that is equals to, we can find if it tries to take the union of C and then the complement. Let's see what we are going to have. So in some way this should give us some nice solution. So we can take it to be probability of C plus probability of C complement and probability of C intersection C complement. Okay, so and that does not equals to 0. So probability of C, as we have proved, that is exponential minus 4, and the probability of complement, that's 1 minus exponential minus 4, and the complement of C intersection C is actually equals to 0, and they give us 1. Okay, so let's check the next question. That is question 6. Question C, if the sample space is minus infinity to infinity, and if C subset of the sample space is a set for which the integral ds exists. So we have to show that this set of a function is not a probability set function, and then what constant do we multiply the integrand by it to make it a probability set function. Don't forget our probability set function for the entire sample space has to be 1. So we want to show that this equals to 1. If it does not equals to 1, that means that this probability set function, this set function is not a probability set function. Okay, so let's check. So probability of the entire space C equals to integral minus infinity to infinity exponential minus mod x dx. So we have gone to split this because of that mode. So then move from minus infinity to 0, that is negative. So if this is negative, then our mod s will be minus x dx, then plus from 0 to infinity. So for the positive side, our mod will be x dx. Okay, so if we simplify this, we have 0 exponential x dx plus 0 to infinity exponential minus x dx. So if you integrate this, we have exponential x minus infinity to 0. Then if you integrate this, then we have exponential minus x minus s 0 to infinity. So then we have exponential 0 and exponential minus infinity plus minus exponential minus infinity minus exponential minus 0. So this is anything which power 0 equals to 1, this decays to 0. Then this exponential 0, this also decays to 0. And then we also add this to be 1 minus 1, then we have 1 which equals to 2. So since this is not equals to 1, so this is not a probability set function. So in order to make this probability set function, so to make this is set a probability set function, then we have to multiply it with 1/2. So that means that 1/2 integral minus infinity to infinity exponential minus mod x dx will actually give us 1/2, which will actually equal to 1, which is a probability set function. So that's a nice question. So we can now move to question number 7. So let's see what we have. Question number 7. We have if C1 and C2 are subsets of the sample space, we have to show that the probability of the intersection of C1 and C2 is less than probability of C1 less than the union. And so let's pick this inequality one after the other. So let's pick this first part. So we have C1 intersects C2. So this C1 intersects C2 means that it only takes some part of element of C1 and then C2. That means that this should be subset of C1. Okay, because this equation is an intersection which may not necessarily take the whole of C1. So this should be a subset of C1. An intersection must include elements of C1 that is common to C2. So there exists an element in C1 that's also in C2. So that means that C1 intersects C2 is a subset of C1. Then by monotonicity, the probability of C1 intersection C2 will be less than probability of C1. So that completes that proof. So for the next inequality, we also have that C1 is a subset of C1 union C2. The set of these will contain some element in C2 that may not necessarily be C1. Okay, but every element in this, every set in C1 and union C2 must also contain all the elements in C1. So that means that C1 is smaller than this, and then it's contained in this. So also by monotonicity, the probability of C1 to be less than probability of C1 union C2. So the next one is show for these two. So also note C1 union C2 is also a subset of C1. Okay, we have to pick this out together. So for that, so probability of C1 union C2, that is equal to probability of C1 plus probability of C2 minus probability of C1 intersection C2. That's by the law of inclusion. Since we know probability of C1 intersection C2 must always be greater than or equals to 0, that's part of the properties of probability. That means the probability of C1 union C2 will be greater than or equals to probability of C1 plus probability of C2. So that will be less than, because there are some parts, there are some element that is greater than 0 that is being subtracted from this portion. So then this inequality holds. So we combine everything together, then we are done with the proof. So then we move to the next question. So let's see what we have in the next question. We have the C1, C2, C3, B3 mutuality change subset of the sample space, and we have to find the probability of C1 union C2 intersection C3. Don't forget the definition of mutuality strength means that intersections of any of the two sets are empty, which is 0. So let's start with the first one, probability of C1 union C2 intersection C3. So by distributive law, we are going to have probability of C1 intersection C3 union probability of C2 intersection C3. Okay, the probability of C1 intersection C3 plus probability of C2 intersection C3. And then since they are mutually disjoint, this is the probability of empty set, the probability of empty set, and that is equal to 0. So by mutually disjoint, the intersection of these two is empty. Alright, so then let's prove the second one, C1 complement union 2 complement. So by De Morgan's law, we have this. There will be C1 intersection C2 complement. Okay, and that is equal to 1 minus P C1 intersection C2 by definition of complement, and that is equal to 1 minus, since C1 and C2 are mutually disjoint, equals to empty set, and that's equals to 1. And that completes that proof. Okay, so let's check question number 10. So for Question again, we have a bowl containing 16 chips, of which 6 are red, 7 are white, and 3 are blue. There are 16 chips, 6 are red. We have 6, 7 are white. And then this, okay. Let's clean off 7. And then we have 3 are blue. Make it 16. So if 4 shifts are taken at random without replacement, find the probability that each of the 4 shifts is right. So the best way to handle this question is to make use of combination. So that means that the total number of outcome is 4 shifts. That's 16. Then we pick 4. That's 16 combination 4. So the first question A, each of the 4 shifts is red. Then we have how many reds do we have? We have 6. Out of this 6, we pick 4 over 16 over 4. Then that is equal to 6 combination 6 minus 4 over 16 combination over 16 combination 16 minus 4 combination. So you can actually factorize this. Okay, so you can actually undo this carefully and then get the desired result. Alright, so this is 4. This is 4. So if you get this, we have 6 factorial over, so your numerator, if you make use of your calculator, anything that should be 15, then over 1820. So you're gonna get, you can approximate that. So B, none of the 4 shifts is red. So none of the 4 shifts is red. So if we remove 6 out of the whole equation, we'll be left with 10 balls or 10 shifts to pick from. That means that out of 10 we pick 4 over 16 combination 4, and that gives us 10 factorial 4 factorial 10 minus 4 factorial divided by 16 factorial over 4 factorial 16 minus 4 factorial. Then you can also verify the solution of this. This should give you 21 over 180. So the next question is, there is at least 1 ship of each. At least 1 ship of each. That means what? That means that we have 1 black. Sorry, there's no black in the equation. Maybe we have 1. And then we have 1 white, 1 red, and 2 blue. Or we can have 1 white, 2 red, and 1 blue, because they have to be 4 in numbers. Or we have 2 white, 1 red, and then 1 blue. So then we sum everything up. So now that the probability, then we take this, then we make this to be event of A. The probability of A will be equals to, by the first one, how many whites we have? We have 7 whites, so 7 whites, pick 1. The how many red? 6 red, pick 1. The how many blue? 3 blues, pick 2. Or 1 white, 7 pick 1, 2 red, 6 pick 2, 1 blue, 3 pick 1, or white, 7 white pick 2, 6 red pick 1, and then how many blues? We have 6 blues, 3 blues rather, pick 1. So everything over 16 picked 4. So you can carefully check the solution of that and compare your result with this 819 over 1820. So I think that completes that question. So the next question is question 11. Question 11, we have a person has purchased 10 of 1,000 tickets sold in a certain raffle. To determine the first prize winners, 5 tickets are to be drawn at random and without replacement. Compute the probability that this person wins at least one prize. So we are given a hint. First, compute the probability that the person does not win a prize. Okay. So since we have 1,000 tickets, so out of this 1,000 tickets, you want to draw to determine the 5 prize winners. 5 tickets are to be drawn. So the total outcome, or what we can call the number of ways, number of ways to choose this thing. So we have 1,000. They want to pick only 5. So probability that does not win a prize, that means that what's the probability that we are going to draw the 5 tickets out from those tickets that the person does not purchase. So the person purchased 10 tickets. So if we subtract 10 tickets from 1,000 tickets, then you'll be left with 919 tickets. So we have now 190 tickets to pick from, so that the person does not win any prize. So, and this gives us the probability that the person does not win a prize, because none of the 5 tickets will be drawn out of his own 10 tickets. So the probability that he's going to win, probability that the person win at least one prize will now be equals to the complement that does not win, which is equals to 1 minus combination of 919 or 5 over 1,005. So you can also confirm the result of this, and this should give you 1 minus 0.951, and that should be equals to 0.049. Okay, so you can just try to confirm that solution. Likewise, so let's check question number 12. So for question number 12, we have compute the probability of being dealt at a random and without replacement of a 13 card bridge and consisting of 6 spades, 4 hearts, 2 diamond and 1 club, and then 13 cards of the same suit. So now in the card we have 52 cards. So then out of 52 cards, wants to pick 13 card. Okay, so let event A, let A be probability of 6 spades, 4 hearts, 2 diamonds, and 1 club. So probability of event A will be equals to 6 spades. We know that we have 13 spades in the club, so we have 13. We pick 6 hearts, we have 13 hearts. So out of 13 we pick 4. Then diamond, we have 4 diamonds. We have 13 diamond likewise. Then we pick 2. Then in club we have 13 club of cards. Then we pick 1. Everything over 52. Combination 13. Then we check the results of these. If you compute this, then so that should give you something. So you can try to confirm this. This is approximately 0.951. So you can try to confirm the results. So the next one is that probability of being, let's be the 13 cards of the same suit. So and then in the cards we have 4 suits in the card, right? So that is 4 types of card that we have. Spade, a spade is a suit, spade is a suit, heart is a suit, and diamond is a suit, and the club is a suit. So those are the 4 suits we have in the card. So then out of these 4 suits we pick 1. Then after picking 1, then we pick 13 out of 13, and that is 1. So we have 52 over 13, and then that gives us 4 combination 1 over 52 combination 13. So if you also solve this, then this is kind of small. That's 4 over 6.35 times 10 to the power 11. So you can finish up this, and that completes the result of that. So in the next video we try to complete the solution in the next video. So hope to see you in the next video. Thank you.